remember in my first job as a software engineer seeing all these frameworks, methods and tools that seemed to me at the time to be incredibly complex. But I love to learn and expand my knowledge, and I adopted them, and over the years I watched businesses grow to recognise the importance of building reliable systems that provide an awesome user experience that scales with traffic. These days, by harnessing best practice in the way we build modern applications, we don't have to manage any hardware, and we very rarely get P1 or P2 alerts. The engineering industry grew, and a set of guiding principles known as the 12-factor app were laid out by some of the top experts in the industry. And if you haven't yet integrated them into your engineering team's workflow, it's probably costing you more than necessary, or you're having frequent incidents or outages. So in this video, I'm going to share some of my expertise with you and talk about the 12 things that you can do to ensure that you achieve excellent website or API or application reliability, and set up your application to be massively scalable and reduce your costs. And this is what's known as application modernization. Hey everyone, so why might you want to consider application modernization? Well, it can save your business a huge amount of money by reducing engineering time and improving scalability and the reliability of your application and improving your overall engineering processes. But first, I want to mention why, if you're on dedicated servers, you should consider moving to the cloud before or while you work towards app modernization. If you're managing your own servers, think about all the time that's spent purchasing, managing, provisioning hardware, installing software, upgrading software versions, managing security, and decommissioning old hardware. It adds up to a significant amount of time. And if you move to the cloud, you'll manage less and can focus on features rather than maintenance. When it comes to app modernization, you will improve your brand perception. A more reliable service will make your services better, you'll avoid downtime, and make your customers happy with a great service. And for marketing websites, you can ensure you never miss a lead or send paid traffic to a site that isn't working. You'll be able to launch features easier and have a happier development team, and you'll reduce your overall risk because you'll have better processes and will be able to recover from incidents faster. The goal is to make your web service a smooth and efficient marketing or revenue source, i.e. no version mismatches between environments that can lead to a lot of wasted engineering time. A better user experience for customers means happier customers who will be more loyal and lead to an increase in revenue. But there is a solution, which is a series of steps to follow. It starts off by auditing what you have to get a clear picture. This can be done through infrastructure maps for the architecture, domain maps for the services and functionality, and technical reviews to understand the detail about what's running on each server. Then you need to understand your critical user path and to design your SLA and decide the SLOs you want to design for, as a 99.9% uptime SLA would be quite different to a 99.99% uptime SLA. It's basically the difference between 43 minutes versus 4 minutes of downtime per month. Once you've designed your SLA, you know what you're targeting. There is a guiding set of principles for modern application development that ensure the most agile, scalable and effective outcome for your web service or website. And these are known as the 12-factor app. This is an official standard we've used for years to build highly scalable sites and web applications handling millions of visits per day. The first thing is that you should have one code base, tracked in version control, and many deployments. This enables you to make rapid changes by ensuring your code base is versioned. Now combine that with a CI/CD tool, or continuous integration or continuous deployment tool, to automate your deployment, and you can quickly release new versions of your software. Because of version control, you can roll back to an earlier deployment if you need to, and you can also see what changes may have led to an incident. The second thing is that you should explicitly declare and isolate dependencies. So all first and third party dependencies should be declared in a package file, such as a composer.json for PHP or a package.json for Node.js. This ensures that you can load them in when you have to, and that isolation means you can replace them if needed. Now those dependencies are put into the codebase and tracked in version control, so if you do subsequent deployments you can roll forward or roll back, and you can always make sure that you have that consistent library of dependencies for any version of the application. So if you change something over time, you'll make sure that that changes with the application, and if you need to roll back, you'll undo that change. The third thing is that you should store config in the environment. By putting the config in the environment and not in the code, it lets you quickly spin up additional environments as needed, so that if you need another environment for UAT or stage or production, you can quickly spin up another environment because all the environment variables are attached to that environment and not in the code base. You don't have to make any code changes. The fourth thing is that you want to treat backing services as attached resources. Attached resources are things like databases, queues, SMTP, file stores and APIs that your services use. Basically, you want to be able to swap out attached services quickly by making changes to the environment config without having to make changes to the code. Now, as an example, if you were using AWS for production, this would let you swap out a local MySQL instance that you were using locally for an Amazon RDS instance that you intend to use in production. Now, talking about environments, the fifth thing is that you want to strictly separate build and run stages so that you can have separate environments in which to perform different actions, such as a local development environment, integration testing, user acceptance, and production environments, all separated so that they don't collide with each other as they're being used. The sixth thing is that you want to execute the app as one or more stateless processes. Now, statelessness means you're separating processing from data. An easy way to think of this is that your app can be destroyed and recreated and the data still remains intact. Now, this could be a Docker container for your code connected to separate databases or file stores, but basically you should be able to destroy and recreate that application processing container and the app should continue running as normal. It also means that when you need to scale up, you can have many stateless containers accessing that same database and file stores, allowing you to serve a greater amount of people with your application through more processing containers. Now, you'll need something to handle all that container orchestration, that is the spinning up or shutting down of those containers. So that's where a tool like Kubernetes or Google Cloud Run will come into play, and that will handle that spinning up and shutting down of those containers for you. And the seventh thing is that you want to export services via port binding. This allows you to ensure that there's only a specific port that can access your stateless services. For example, this could be port 80 for a web server, and your routing layer will handle the SSL security, and your load balancer will share the traffic against the many instances of that web server container. The eighth thing is that you want to scale out via the process model. Now, this is where your stateless containers can scale to handle the demand. This is what enables concurrency in your application. It allows you to scale up your service to meet demand as each stateless container handles one type of process. For example, HTTP requests may be handled by a web process, and a long-running background task such as generating reports or re-indexing a database can be handled by a worker process in the background. Now, what that means is scaling up now becomes a simple action to monitor the load a particular process or a type of stateless container is getting. Now, the ninth thing is that you want to maximize robustness with fast startup and graceful shutdown of those containers. You want to make sure that your containers can spin up fast and shut down gracefully. If they spin up quickly, ideally in seconds, then you'll be able to quickly meet rising demands due to an increase in requests or traffic to your service. You also want them to shut down gracefully so that any current processes finish processing, or in the case of background tasks, returning their job to the queue and then the container shuts down. So there are no hanging processes or partially processed data, and users have a good experience without being cut off from the action they're performing. Now, the 10th thing is a real-time SAP if you're not getting it right, but basically you want to keep all your development, staging and production environments as similar as possible, so that all the developers and each environment, so UAT, production for instance, they're all using the same versions of software and all the dependencies so that it's always consistent. Now, we expect that engineers will be developing on their local machines, but that's where you can use a containerization tool such as Docker to ensure consistency between local development and production. So you're using the same version of MySQL, for instance. And for those environments, keeping them as consistent as possible in both architecture and dependencies will ensure that you don't hit any surprises when you're moving previously approved code to the next environment. In conjunction with CI/CD tooling, this consistently should allow engineers to take on more responsibility when it comes to deployments. The 11th thing is to treat logs as event streams. Logs provide visibility into the behavior of a running app. Now, by default, these write to the local file system, but what you want to do is convert that into a stream of aggregated time-ordered events collected from the output of all running processes and backing services. They're typically in the format of one event per line. Now, all of those logs should write to standard out rather than the local file system, and this is what enables them to be watched in real time or picked up by an external log indexing and analysis system for easy access and incident diagnosis. And it helps you keep your containers stateless because you're not storing that log data inside the container. Remember, we want that separation between processing and data in our containers. That is what enables us to scale. Now, the 12th and final thing is that you want to run admin and management tasks as one-off processes. Now, those processes are the things that are secondary to serving users, such as running reports in the background, consoles, database migrations, or one-time scripts. Each one of those processes should be run against a new instance of that container instance that's identical to the environment of the regular long-running process of the app, such as the web server, for example. But this ensures that the standard processes are not affected by those background tasks. So you might be wondering how this looks from a technical implementation perspective. Now, I'm going to use Google Cloud as the example here, but you can do the same on other cloud providers such as AWS and Azure by using similar services. And at Firney, we work across all three of those platforms successfully. But for simplicity, I'm just going to talk about how you would do this on Google Cloud. Now, it's important to state that there isn't really a one-size-fits-all approach here, as each business will have different services with different staff motivations and different customer needs. Let's use this theoretical example of a simple web service that is hosted on a dedicated server with a web server, PHP, database, and Redis for caching and queues, and all that software is installed on the one dedicated server. Now, this theoretical business wants to move faster, but has had a variety of issues from slow responses, downtime, unreliable services, slow feature development, and a lot of knowledge has been lost when certain members of staff exited the business. Now, they've audited what they have, documented the SLA they would like to meet, which is a 99.9% uptime, and they're now looking to improve their setup. So we'll talk through how we would modernize the app and make it more reliable and scalable. First off, you want to ensure you make each service immutable, so they can be destroyed and restored rapidly, and you have an image of each service. To do so, we would migrate them to run as containers using a tool such as Docker, or using serverless tools such as Cloud Functions or App Engine for more simple microservices. And now we have stateless containers for the web server, PHP, Redis, and MySQL image, which will only be used for local development, but I'll come back to that. And we'll make sure that any data is stored on separate services, such as in the database, or use a network file share or cloud storage for files and logs. And remember, separating that data and processing is necessary, as we want to be able to freely destroy and restore the processing services without losing any of that data. We'll also make sure that we have backups for those data services so that we can restore those if needed. Next, you would need infrastructure to run those containers on, such as Kubernetes or Google Cloud Run. And for the databases, we don't really want to be managing dedicated servers for those databases. So we can use something like Google Cloud SQL to manage that MySQL database. And that means we don't have to manage the hardware for that database, thus saving time and money. Now, we can create a container for Redis and the queues and caching, and we'll host that on Kubernetes. There are other ways of doing that. And we'll put a load balancer in front to distribute the traffic amongst those containers that get spun up. And we'll also put a content delivery network to handle caching of static assets such as images. Now, all services will have failover to another region. And in Kubernetes, we'll add namespaces for a staging and UAT environment so that they all use the same setup and we don't have any differences between those environments. For our local developer setup, we'll use the same Docker containers that we're going to use in production for the web server and Redis, but as we're using a serverless Cloud SQL solution for MySQL, we'll also use a Docker image locally with the same version of MySQL that we're using in the cloud production environment for local development. We also have to make sure that all our code is deployed consistently, so for this we're going to use Harness to connect to our GitHub repository and handle all the deployments. And we'll make sure that all containers are logging to standard out, and we can ingest all of those logs into New Relic so that they're searchable and we can delve into any incidents if we have to. So we end up with a solution that looks a bit like this. And we'll also set up an incident support team with a managed cloud support layer to respond to any alerts we get from the observability stack. The Managed Cloud Support team will serve as an escalation point for our internal team and support our internal team with the solution as it's designed and built. So what did we do? Well, we moved our application off of a single point of failure dedicated server, and we made our solution immutable so it can be destroyed and redeployed with a single click. We set up consistent environments so that we can reduce human error in deployment, and we set it up as a scalable solution, and it can also be redeployed for other customers or projects or to other cloud providers. And we reduced the amount of hardware we have to manage by putting everything in the cloud. We set up monitoring alerting for our stack, and we made sure that we have sufficient personnel in place to support the solution. And of course, we'll make sure we document everything as we go so that anyone joining the project can quickly understand how it's built. There's a lot more you can do. This is just the first step of the journey. If you're interested in learning more and taking your business down the path of application modernization, then please reach out to us via the contact form, which I'll link to down in the comments. Now, we're going to be delving into those 12 factors in more detail in future videos, but I hope that was helpful. Please like the video if it was, share it with anyone you think could benefit, subscribe to the channel for more helpful cloud and engineering tips and advice, and I'll see you in the next video.